In this video, we're going to use the fundamental theorem of calculus 2 to visualize things from a new perspective. So when someone states the second fundamental theorem of calculus, think about this diagram in your mind. So visualize this diagram in your mind where x can slide back and forth. Okay. So the second fundamental theorem of calculus, if you differentiate the area, which is this bit here, if you differentiate the area, it will give you the original function itself. So, second fundamental theorem of calculus. When given this, you can differentiate the area and it will be the function itself. It will be this. So, the second fundamental theorem of calculus, when given this, you can jump to here. Okay? But now in this video, we're going to be given this, and then we're going to jump backwards to try and deduce things about the original function. It will make sense later on, I hope. So second fundamental theorem of calculus 2. When given this, you can jump to here. But then when given this, you can also work backwards to find out the original function itself. So, for example, suppose well, looking at this here, if someone gives you y prime equals something, then you can work backwards to deduce things about the original y itself. Okay, so here, if someone gives you y prime equals something, you can use this and jump backwards to deduce things about the original function, the original y itself. So, for example, just remember that second fundamental theorem of calculus 2. This you can jump to here. So when given this, you can jump backwards to find the original function itself. So, for example, if when given this, let's say y prime. So when given y prime equals this, when y prime equals this, what can you tell me about the original y itself? Okay, so whether on a separate occasion, on a different note, just remember that when you differentiate log of x, it gives you 1 over x. So basically, this is what I've given you here, and then jumping backwards is really the natural log of x. Okay, just bear that in mind. So let's start again. When given this here, so when given this here, so that's like me saying this. I've got something where the derivative looks like this, 1 over x. Okay, when the derivative looks like this, so us jumping backwards, the original y would be so it would be natural log of x, but well, absolute to be precise. But let's pretend we didn't know this. Okay, so when given this here, we can jump backwards, but instead of visualizing as this, visualize it like this. Visualize it as when given this, when given this here, we could visualize it as natural log of absolute of x here, but let's not visualize it like that. Let's visualize it like this. It will allow us to see new things. Well, anyway, when given this here, visualize it as this. So hang on, let's start again down here. So when given this, visualize it as from a to x, the original function itself, but we got to use a t because we don't want it to clash with this x dt. Okay, so when you look at this here, hang on. So don't forget this is like don't forget this is like the natural log of x. So natural log of x, well, it should, but to be precise, is absolute x. So it would be like this. Let's double check everything. So here it's going downhill, 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 and it gets really, really steep. So let's look at the derivative. Well, the derivative is going downhill, downhill, and it gets the gradient gets very, very big quickly. So on the negative side, it makes sense. And looking at the original function, it's climbing really, really steep here. Really, really, it's climbing. It's going uphill all the time. But then it gets shallower and shallower and shallower. Let's check the derivative. It's really, really steep, and then it gets shallower and shallower, and so on. So the derivative makes sense. But the thing is, now visualize this well, hang on. This here is the natural log of absolute of x. But let's forget about the absolute of x for the time being. Let's just concentrate on the positive side. So let's forget about this for the time being. Okay, let's just look at it on the positive side. Hang on, let me just redraw this. So it looks something like this. Okay, natural log of x. So this bit here is nice and easy. It's 1 here, and then this here is 0. We've done this in the past. So let's take our a to be at this convenient point 1. Okay, so this bit here is 1. Now suppose you want to know what is the natural log of 9, say, a random place. Let's say 9. So the natural log of 9, you would look at your natural log graph, which would be this thing here. So 9 would be here. So what is the natural log of 9? It would be you starting from here, jumping to here, and reading it from here. Here's another perspective here. Hang on, 1 over x looks like this. Let's say. So one. What is the natural log of 1? So what is the natural log of 9? Well, looking at it, using this to see it from a different using this to see it from a different perspective, starting from 1, going up to 9, going up to 9 here. Okay, so that would be the area from 1 to 9. So that would be this area here. Okay, so what is the natural log of 9? The natural log of 9 is really the area from 1 to 9 of the reciprocal graph. So this thing here allows us to visualize the natural log in terms of area of the reciprocal graph. I will elaborate more on it in the next video. Okay.